All right, physics people. I want to come back to this problem real quick that was just in the previous video. I want to highlight something for you and then show you a slightly different way of looking at what's happening. It's important to note that the amount of energy really doesn't depend on this trajectory. We really don't know anything about that trajectory. We don't know its maximum height, for example. We don't know this horizontal distance. We don't know a launch angle off of the baseball bat. But we can still find a final velocity, and it doesn't require diving into the horizontal and vertical components of this initial velocity, and therefore using kinematics with the vertical stuff and constant motion equation for the horizontal stuff, and then recombining things. Using this is actually, if you consider what we've done, it's a simpler process evaluating that final velocity using our knowledge of energy and conservation of energy. Simpler than it would have been using the traditional projectile motion types of equations. Also, I want to show you a slightly different way of viewing what is happening, what is taking place here in terms of just the energy. So we know that, let's take a kind of a visual look at the initial and the final situations. And I mentioned in one of our previous recent videos that this really is just accounting. When energy is conserved, then we just have to account for all of it, regardless of where it might go. So I'm going to put a slightly darker line here. There's not going to be any thickness to this line that's meaningful. I just wanted that to show up here. We're going to have an initial value of kinetic energy when that baseball comes off of the bat. We're going to have that location of the ball right when it comes to the bat be our reference level or our origin, right? So there is no potential energy. There's 0 joules of potential energy there. And what we found was our initial amount of kinetic energy turned out to be, actually on the next page, 97 joules. Excuse me. So we have 97 joules of initial kinetic energy. And what we know is that the initial is going to equal the final, since everything is conserved. But we've lost some kinetic energy, and the reason we have to say that we have to account for that is the fact that we've gained some potential in the final situation. So here's a kinetic versus potential comparison with our final information. And the final information, what we know was that we gained an amount of 11 joules of potential energy based on its final position, based on this 7-meter height difference here in this final position right before it was caught, or right when it was caught, maybe we could say. Well, now we have to account for these 11 joules. Where could they have come from? They did not come from this amount of potential energy. There was none. They had to come from this. So this amount of kinetic energy is reduced by that 11 joules, and here's your 86 joules of kinetic energy when it is caught in the final condition here. So you'll see little bar graphs like this come up again later on for us, and it's not a bad way of viewing what's happening. We had to take away this 11 joules to convert it into that stored energy, stored in the position of the ball compared to its initial position. So a visual way of looking at what is going on with the energy in that problem. Now I want to examine another problem here. And this other problem is going to involve an interesting thing here. So, new situation, completely new. We're going to look at a snowboarder, and the snowboarder might be cruising along on horizontal surface, and since it's snow, we've got No friction. Snowboard, right there. But the snowboarder cruising along is going to encounter a rise in elevation, and then the ground goes horizontal one more time. So from here to here, there's an increase in height. And we can make a note of that here. Let's call that H. And here's what we're going to do. We're going to say that the snowboarder, we're going to say, all right, let's give it a velocity of 4 meters per second. And when this initial velocity in this direction is 4 meters per second, when they get up this little hill, they just have enough energy to make it to the top. And once there, they stop. Velocity becomes 0. All right. So here's the question. How fast will the snowboarder be going at this higher elevation if instead of 4 meters per second, they're traveling 5 meters per second? So we're going to switch this up, and we have a different initial velocity of 5 meters per second. And so maybe I can mark this as initial, and I have to mark this as initial. Here's a final that matches this initial. And what I want to find is how fast this snowboarder is going at the higher elevation here. And so this final velocity that would correspond to that initial velocity. How am I going to work that out? What you're going to want to do right now is hit pause on the video, and I want you to think of a quick strategy. What are you going to do to figure this out for yourself? Okay, pause, and back on. Game on. Here we go. So, what we need to do first is understand what we can figure out with the information we have. This change right here, it's possible to look at it from looking at this to this and seeing the change here, and use that to allow us to make a change from final to final. But it's going to be a little less confusing if we sort of take a more methodical approach. And the more methodical approach actually involves us finding this height. We're going to use our first scenario, 4 meters per second, and then stopping just as the snowboard gets to the top to find this height. What we're going to do then is use that height in our new scenario with an initial speed of 5 meters per second. So how is this going to look? So finding H. That's our job right now. And what we know is that it's snow. There's no friction. Initial and final mechanical energy will be equal. Energy will be conserved. So we set this up. Initial kinetic plus initial potential equals final kinetic plus final potential. And so you can see right away we're going to have speed coming into play at the lower elevation and speed coming into play at the higher elevation, possibly. The height coming into play at the higher elevation. And what we're going to do is we're simply going to say that this reference line that I've marked off here at this lower elevation, that's going to be our origin. That will be 0. Or y equals 0. Or we're using h, where h equals 0. Okay, fine. Easy enough. So now, where does that take us? The initial kinetic energy is going to be a 1/2 m vi squared. The initial potential energy is going to be an m times a g times my initial height, which is actually going to be 0. So times 0. That's going to go away. Done. My final information. So in this case, I've got kinetic energy 1/2 m v final squared. But I've already said that with this first scenario, my final velocity is 0. I have no kinetic energy for my first scenario here. So this goes to 0. And what I do have is a final potential energy, m times g times h. Well, it's really cool. A couple things disappeared. About half the work we might have done is just gone for us. And I can see my unknown. I can see the goal right here, the height of the top of the hill. I'm going to solve this for h and then plug some numbers in. So with our canceling, and there's a little bit more canceling we can do, you can see that mass disappears from the equation because it's found in all these terms. And so our equation for h ends up becoming velocity squared divided by 2g. So what velocity is that? Well, it's the only velocity around. It's our initial velocity here. And I can plug some numbers in, and my initial velocity was 4 meters per second. That's going to be 4 squared. And I'm divided by 2 times g. G is the 9.81. So I get a value for h. 0.82 meters. Awesome. So remember, now that I know that, I'm going to use this knowledge of the height and my new initial velocity to find what the new final velocity would end up being. And I'm going to warn you, we're going to see something that's not exactly very intuitive at first. You'll see what I mean. So here we go with that. We're going to see that we're going to find a final velocity from h and all the other stuff. Okay. Going back to conservation of energy. Initial mechanical equals final mechanical energies. Again, we got the breakdown. Initial kinetic plus initial potential equals final kinetic minus, plus final potential. Oh, keep your pluses and minuses straight here. And now, interesting thing, we know again that since this lower elevation is our reference, that's our origin, h is 0, there is no stored potential energy initially, so that term goes to 0, goes away. My initial kinetic, 1/2 m initial squared, and that's 0. And my final kinetic, 1/2 m the final squared. So I can see the goal already showing up. The final potential energy, mgh. And I know h this time. My unknown is here. That's the goal. That's what I want to find. Rearrange this a little bit, and I'm solving for final velocity. And I get an equation that looks like this. And it's going to look familiar to you. It better look familiar to you because you're responsible for knowing how this one works also. Initial velocity squared minus 2 gh. If I were to square both sides, I'd get final velocity squared equals initial velocity squared minus 2g. And h really is not just a single dimension. It's a change in position. Maybe I should make a note of that. H really is a change in y values. That should look a little familiar too. That should help us out a little bit. So really we can think of it as a displacement in the vertical direction. Awesome. So we're matching one of our big 5 kinematics equations. Doing that again. After plugging some numbers into this equation, we actually get, it turns out to be like 2.99, so that's going to give us 3 meters per second for the final velocity. Now the thing I want to point out to you that is the non-intuitive part here is that when we made this change, we went from 4 meters per second as our initial condition to 5 meters per second, right? That was an increase in 1 meter per second. What we saw was that we went from a final velocity of 0 meters per second to a final velocity of 3 meters per second. So it's not a one-for-one match. And if you delve into the equations, you start to realize that energy depends on, sorry for the brief interruption here from the announcement.
The French Cafe
energy depends on the square of the velocity. And if we're looking at a change in energy, we're looking at a difference in not velocities, but a difference in the squares of the velocities. And so we're going to see not a increase of 1 and 1, but an increase of 1 and 3. And it does work out. There's one of the conceptual checkpoints in this section that goes through this, and they do a pretty good job of explaining that difference, that distinction, and why you see this instead of expecting to see a 1 here. That's it for that example, and hope it's making sense to you. More may be coming your way. I will let you know. Thanks for watching.